Welcome to this presentation on the fundamentals of microwave communication of the subject microwave and radar of 5th semester of electronics group. Myself Sanjit Kumar Singh, lecturer in electronics and telecommunication at Praveen Patil College of Diploma Engineering and Technology. So topics to learn in this presentation: microwave frequency bands and the spectrum range, the band designations, applications and microwave in various fields, comparison of waveguide and transmission line, types of waveguides, particularly the rectangular and circular, propagation of waves in rectangular waveguides. Then expected outcome after going through this presentation are: use specified waveguides in microwave communication system, summarize the range and application of the given microwave frequency bands, compare the given parameters of the waveguide and transmission line, and calculate the cutoff frequency of the rectangular waveguide. So here it is. First we must understand what is microwave signal. So microwave is a region in the electromagnetic spectrum in the frequency range from 0.3 gigahertz to 100 gigahertz, or even extended up to 300 gigahertz. This corresponds to a wavelength from 30 centimeter to 0.3 millimeter in free space. The entire range of frequencies of microwave region from 0.3 gigahertz to 100 gigahertz is known as microwave spectrum. So under this, it covers the range frequencies of UHF, SHF and EHF. In the adjacent figure we see the different micro frequency bands and the respective frequencies as well as the applications. Here are the different microwave band designations with the frequency ranges and the applications. So there are L, S, C, X, K, U, K, K, Q, U, V, E, W, F, D. Yeah, these are the different wave band designations with the respective frequency ranges are given, and the corresponding wavelength we can see, and the applications. So applications, there are a number of applications of microwaves and microwave communication. It is used in the military, telemetry, GPS and mobile phone. The L bands are preferred. Weather radar, surface ship radar, communication satellites, microwave ovens make use of S band, that is 2 to 4 gigahertz. For C band, the most widely used C band 4 to 8 gigahertz is used for long distance radio communication. Then X band 8 to 12 gigahertz is used for satellite communication, radar, terrestrial, broadband, space communication and amateur radio. Then Ku band, that is 12 to 18 gigahertz, is used for satellite communication. K band for radar and satellite communication. So there are a number of bands and respective applications are given in this table. We can move on. Next, the comparison of waveguide with transmission line. How waveguide is different or similar to a transmission line. So first we must understand what is a waveguide. A waveguide is a hollow metallic structure through which electric and magnetic energy are transmitted, whereas transmission line, a conductor which is used to carry electrical signal from one place to another. Waveguides operate in either TE or a TM mode, out of which TE10 is the preferred mode, that is the dominant mode. Operating modes in transmission line are TEM or quasi-TEM mode. Operating frequency in waveguides is from 3 gigahertz to 100 gigahertz. Operating frequency in transmission line is few megahertz range. Then power handling capacity is very high in waveguide, that is a merit point. Power handling in transmission line is low to moderate. Waveguides acts as a high pass filter, whereas transmission lines they can pass through all the frequencies and mostly they act as a low pass filter. Wave theory is used for propagation analysis in waveguide, whereas the circuit theory is used in transmission line for analysis. Impedance range is 100 to 500 ohms in waveguide. Impedance range is 10 to 100 ohms in transmission line. Velocity of propagation of waves is less than free space in waveguide. Then in transmission line it is almost equal to the free space velocity. Manufacturing requires high precision and costlier apparatus. Manufacturing is comparatively easier in transmission line and less costly. Power losses are less, whereas in transmission line power losses are more. So these are the comparating points. Now what are the types of the waveguide? There are different types of waveguides: rectangular waveguide, circular waveguide, elliptical waveguide, single ridged waveguide, double ridged waveguide. So out of this we have to study the rectangular and the circular waveguide at a diploma level. Next, the propagation of waves through rectangular waveguide. Propagation of waves through rectangular waveguide can be understood with the help of the diagram in the adjacent. Rectangular waveguide with dimension A as the width, the longer dimension, and B as height, and generally A is equal to twice B. So A dimension is generally 2 times the height. So the aspect ratio beta B by A is kept at 0.5. Dominant mode of operation TEMN here is TE10, where M is 1 and N is equal to 0, where M and N are number of half wave patterns along longer, that is A dimension, and shorter dimension B respectively. When a probe is used to launch energy, microwave energy, into the waveguide, the electromagnetic fields will bounce off the side walls of the waveguide. So in the adjacent figure we can see the electric and the magnetic fields, how they are propagating along the z direction. So both these electric and magnetic fields are, you can see, the perpendicular to each other. Now here you can see the reflection of a wave from a conducting surface. When the incident microwave signal at an angle theta I, it comes out, it is reflected in the inside with the theta r, and this reflection depends upon the operating frequency. At a high frequency the angles are large, the path between the opposite walls is relatively long. At lower frequencies the angles decrease and path between the sides shortens. When the operating frequency is not equal to the cutoff frequency, signal simply bounces back and forth and has no forward motion. The last diagram we can see where there is a upward and downward arrow and is not moving forward in the z direction or along the length of the waveguide. So at this frequency and below, no energy is propagated. Below the cutoff frequency FCO, no energy is propagated into the waveguide. So cutoff frequency is calculated as FCO is equal to 300 by twice A, where A is the longer dimension of the waveguide, rectangular waveguide, and the calculated value is in terms of megahertz. The zigzag path causes a lower velocity of signal in the waveguide than in free space. So what we learned in this presentation, we saw the microwave signal, the band designations, the microwave signals of the order 1 gigahertz or higher, or 0.3 gigahertz to 100 gigahertz, or to some case it is extended to 300 gigahertz range. Then we saw the different bands of the microwave: L band, S, C, X, K, and so on. Then we saw the different types of the waveguide, circular and the rectangular waveguide, out of which we have to study these two particularly. The cutoff frequency we saw calculated as 300 by twice A in megahertz, and then we saw the different frequency propagated through the waveguide and have different reflecting angle. So that's all. Thank you very much.